Hello students, today we are going to learn Zener diode. Zener diode is a special type of diode which is designed to operate in reverse bias. The name Zener is named after American physicist Clarence Zener who discovered the Zener effect. So this is symbol of Zener diode. This Z at the cathode represent Zener diode. If you apply reverse voltage to PN junction diode, PN junction diode will break down after certain voltage. But Zener diode is worked in reverse bias in the Zener breakdown region. So basically Zener diode is nothing but PN junction diode. So first of all we will see normal PN junction diode. So in PN junction diode we are going to connect two type of material, that is P type of semiconductor with N type of semiconductor. So P type of semiconductor is having positive charge carriers because we are adding trivalent impurity in the silicon or any semiconductor which we are using, silicon or germanium we are using. But in N type there are negative charge carriers as we are adding pentavalent impurity in it. So when P type of material is connected with N type of material near the junction, when the junction is formed, what will happen? The negative charge carriers from the N region start diffusing in P region. Similarly, you can see holes also start diffusing in N region. And because of this diffusion, ions form near the junction. So these ions are formed and this region is empty of free electrons. Empty means depleted. So this region is called as depletion region and we are also called this as depletion layer. So in PN junction the depletion layer is formed. The same happen with the Zener diode. So in Zener diode, the doping percentage of the impurities is higher compared to the normal PN junction diode. So the Zener breakdown is depend upon the ratio of the doping material. So in Zener diode, as I told you, we are heavily doping the Zener diode. Because of that, the positive charge carriers at the P type are more compared to the positive charge of the normal PN junction diode. Here also the same process happen. The electrons from the N region start diffusing to the P region and here depletion layer form. Only difference is that as charge carriers are very large in P and N region, the depletion layer form in the narrow area. And you can say the width of depletion layer is very small in Zener diode as it is heavily doped. So if you see the electric field in this region, the electric field is in this region is nothing but the potential difference, which is 0.7 divided by the width of the depletion layer. So in normal diode the width is very large one, but in Zener diode the width is very small one. So the electric field around this depletion layer is very high in case of Zener diode, but in normal diode it is very low. So normal Zener breakdown, how it happens? When we apply reverse voltage to the PN junction diode, some minority carriers are present in both the regions. So these are the minority carriers. It is expected that in P type of material, only positive charge carriers are present, but because of some impurities, minority carriers are also present. And when we are increasing the voltage beyond V break, what will happen? These minority carriers get enough energy, or you can say they are getting very large energy and they collide with the silicon atoms. And because of this collision, the outermost electron from the valence band of silicon, it goes in conduction and with high speed it collide with another atom. Because of that, the outer electron from that atom, it also goes from valence band to conduction band, and this process continues and very large heat is produced, and because of that your normal PN junction diode get destroyed beyond voltage V breakdown. But here, and this is called as avalanche breakdown. So in Zener, there are two types of breakdowns. First is Zener breakdown and then avalanche breakdown. Zener breakdown occurs before the avalanche breakdown. So what exact happened in the Zener diode? As I told you, the electric charge in on the atoms of this depletion layer is very large as the width of depletion layer is small. So when we apply reverse voltage to this, or you can say when you apply reverse voltage to this Zener diode, what will happen? The electrons from the outer orbit, they are already at high electric field, so they get energy from this source and they goes from valence band to conduction band. If you see the Bohr's model, you can see that the outermost electron is already is having high energy, and they are under this electric field, so they are already having high energy, and when they get very little amount of energy from this source, from valence band they go to conduction band, and because of that Zener breakdown occurs. So Zener breakdown is, as I told you, it depends upon the percentage of doping of the Zener diode. Manufacture at the time of manufacturing, we can decide the Zener breakdown voltage. So VI characteristics we will see. So VI characteristics is nothing but a graph plotted between the voltage across diode and current flowing through diode. So this is voltage across diode in forward bias, current flowing through the diode in forward bias. This is voltage drop across the diode in reverse bias, and this is the current flowing through diode in reverse bias. So the forward characteristics of Zener diode is same as semiconductor diode, that I am not going to explain here. So different, what is different? Different is the VI characteristics in reverse bias. So in reverse bias, initially very small leakage current is flowing through diode because of the minority carriers, and the Zener effect you can see after the voltage Vz. What will happen after the voltage Vz? The electrons from the outer shell, they get enough energy, already they are possessing high electric field, and they goes from valence band to conduction band. So at Vz, what will happen? A large current will flow through the Zener diode. As we are increasing the voltage, the value of current will increase. But we should not increase the value of voltage beyond certain voltage, because when the current flowing through the diode goes more than Iz max, the diode goes in avalanche breakdown and it will break completely. So this part, that is the current, when current is Iz minimum to Iz maximum, the current flowing through the Zener is in between Iz minimum to Iz maximum. We are calling this region as Zener region, and during this region, voltage drop across the Zener remain constant, that is Vz. This is nothing but a Zener effect which is discovered by the scientist Zener. So this property of Zener diode we are using, and we are operating Zener diode in reverse bias. So we will see the application of Zener diode. Because of its characteristics, we are using Zener diode as voltage regulator. We are also calling this as Zener regulator. So this is basic diagram of Zener regulator. So you can see here, this is V in variable. This variable means fluctuations are present. This is unregulated voltage. And RS is connected. This is nothing but the current limiting resistor. Then Zener diode, we are connecting in reverse bias across the load resistance RL. So as you see the properties of Zener diode, or you have already seen the VI characteristics. So You know that in VI characteristics, the voltage drop across the Zener diode remained constant in reverse bias. So this is in reverse bias and voltage drop across it remain constant. So this constant voltage drop we are applying to the load resistance. So voltage drop across the load resistance is going to be constant, that is Vz, and current flowing through the load resistance, it is also constant, which is nothing but Vz divided by RL. So we have to select the value of Rs such that the current flowing through Rs, that is I in, should be in between Vz, Iz max to Iz minimum. So I in is nothing but this voltage is Vz. So I in is nothing but V in minus Vz divided by Rs. So when this V in increases, Vz is constant, Rs is constant. So I in is going to increase. And the increase in current will flow through the Zener diode. So I in is equal to IL plus Iz. As this voltage drop across the Zener is constant, that is voltage drop across the RL is going to be constant. Because of that, IL is going to be constant. So when V in increase, I in increase, IZ increase, but IL going to be constant. Similarly happen when V in decrease, value of I in will decrease and current flowing through the Zener, it will decrease. So the variation in voltage is controlled and the variation in this input current is controlled by the current flowing through the Zener diode. Only thing is that we want the voltage drop across the RL should be constant. So Vz should be constant and Vz remain constant only in the Zener region, that is from Iz minimum to Iz maximum. So while selecting this value of Rs, we have to select the value of Rs such that always the current flowing through the Zener is in the range of I minimum to Iz minimum to Iz maximum. So this is Zener regulator. So this is all about Zener diode. Thank you.